Okay, so we continue to discuss supervised learning, as I said we will do for at least the first third of this class. And within supervised learning, we just finished talking about decision trees, which are a method for classification. And we ended the previous class by discussing the fact that while decision trees on their own work well, but they are not the top performing classifiers, methods that combine a lot of decision trees can work very well and still are, in some domains, state of the art. So this is something that people actually use in real classification problems, whereas individual decision trees are rarely, I would say, used in practice. They are very good to learn. I mean, I think it's important to learn about them, but not something that you will usually use in practice. On the other hand, ensembles of decision trees, combination of decision trees are being used. And we mentioned 3 different methods. I'm going to talk about 2 of them now briefly. And the third, which is boosting, we will cover in a separate lecture. Okay, so let's discuss a bit or a bit more formally some ensemble methods. For decision tree, and remember, decision tree we learn, as we said, we take the data, the features, and the samples, and we have this recursive method which basically trains a decision tree. So selects a question in each stage and separates the samples based on the answer and repeats until we either stop learning or we exhausted all the features. And as we said, this is a deterministic algorithm. So if you do it multiple times, of course, you will get the same tree. So there's no way to combine trees if you just do the method or if you just use the method we discussed in class. So how can you still get combinations of trees? There are multiple ways. Let's discuss 2 of the more popular ones. One is called bagging decision tree, and the other is called random forest. So basically, bagging is a way to use bootstrap approach. Bootstrap is a way that you take some of the samples each time. So instead of learning the tree from all of the samples, you learn the tree from a subset, a random subset of the sample with replacement. So usually we take 90% of the samples or 80% of the samples. Obviously, when we only use a subset of the samples, we may actually end up with different trees each time we use a different subset because we split or we ask the questions based on the samples that we have at our disposal. So this is called a bagging. And then once you have a lot of trees, once you learn a lot of trees using this idea, write each one on a subset of the samples, you just take a new sample, run it through all the trees. Each tree will give you an answer, yes or no, for a class. And then you combine all of these together. Okay, so this is the idea. And we take bootstrap replications from the samples, and so basically we sample from this data, we use it as training, and we learn a new tree from each of these samples. Once we have a tree, right? So we create a lot of different trees, and once a new sample comes in, right? This could be one decision tree, right? One of them, and we have others for the other ones. And once a new sample come in, we just run it through all of these trees and take either the majority vote, or we can even compute the probability, right? If we treat this as 200 trees, we can have actually the fraction of the trees that vote in one direction. The decision is going to be, of course, the one that selects, or the class that is selected by most of the trees, but we can also say like how confident we are and something and those kind of things. Of course, this is not a probabilistic model, but we can provide a probabilistic interpretation. So this is called the bagging decision trees, and again, it's just a summation or majority vote over the trees that we selected, and each tree is generated using a subset of the sample. So that's one way to do it. And we mentioned last time, another way to do it is rather than going on subset of the samples, you can go on subset of the features. And that will also generate different trees, right? If I am only allowed to ask a specific subset of the questions, then obviously I will get a different tree each time I change the set of questions that I can ask. Okay, so this is bagging. As we said, at the end, you just sum up over all the answers and take the majority. And it seems to work well. I will skip that. Okay, the second approach is called random forest. And similar to bagging, it works on sampling, but unlike bagging, which samples from the samples, basically the inputs, a random forest samples from the features. So basically, let's say we have, I don't know, in biology, we can have, let's say 1,000 genes that we can use as questions. Rather than using all 1,000s, we will use for each tree 100 or 50 or something like that, and build a lot of trees, each one with a different subset, random with replacement of the features. And that, of course, each time we have a random sample, we will get a new tree. And each tree will give us a different, or can give us a different answer for the same sample, because it's going to ask different questions. Okay, so this is the way we inject randomness into the process. Okay, so this is the training data. We have n examples, let's say n samples and m features. Sorry. Right, so now we create the bootstrap, or we create the new samples by choosing, and that actually I mean, there's no theory for that. It's just a matter of doing it. You can either select a subset, which most people do, select a subset of the features for all of the tree, or you can select a subset of the features for each, randomly again, for each node in the tree. So you go here, you have the ability to ask only m of those questions. Or you decide in advance that these are the set of questions that you ask for the tree. Again, either of this will work. The whole idea is just to generate another or a lot of different trees, each one combining different questions from our data. Again, so you can either use, pre-select the subset of the questions for the entire tree, or select it for each node, up to you. And at the end, you will get basically a random tree, because the tree is a function of the set of questions that you're allowed to ask. And this is why it's called a random forest. A forest, of course, a collection of trees, and random is each tree basically is randomly generated by randomly sampling a subset of the questions we can ask. Of course, once we have a subset of the questions, we pick the best question out of this subset. But we don't pick the best question out of all of the possible questions we can ask, just of the specific subset of the questions that we have in this, that we selected for this. Okay, so we do it for once for once for one set of questions, and then we do it for another set of questions, and we do it for another set of questions, and we end up with lots of trees. Each one is going to ask different questions at different nodes, because it cannot ask some of these questions in each of the nodes, just because the way we restricted it. And as before, as we did with bagging, we take the majority vote and decide based on that. Okay, so the outcome is the same. The difference between bagging and boosting is how do we generate the tree. In bagging, we sample from the samples. In boosting, in random forest, we sample from the features or from the questions. Okay, and as I said, boosting is a completely separate approach. We'll get to that. Right, so this is some performance measures, right? So if you're allowed to, right, so it says that if you're allowed to select a lot of questions, the trees will end up pretty similar. So that's fine, but of course it depends on how many questions you ask. And this is some type of a random forest for biological questions if you want to ask. Okay, so this is the idea of random forest and of bagging. I would just say, so in terms of bagging, usually we go in practice, what we do is we usually select 80 or 90%. If you select more than that, the trees will be too similar. So that's like if you go to 99%, obviously the trees will be very similar. 80% seems to be fine. If you go much lower than that, then the trees won't be as good as they can be, of course, because you have less samples. So bagging usually is on the order of 80%. In terms of random forest, so there is no good, of course, number for the features, but most people, or in most applications, you usually go for square root if you have enough features. So for each tree, you select the square root of the possible features, and you do it multiple times, hundreds of times, and okay, but this is just what people do in practice. There's no proof that this would be the best. You can play. Okay, so this is it for Ensemble. And as we said, Ensemble or methods that combine different trees or combine a lot of trees usually work almost always work better than a single tree, but more importantly, they are competitive with some of the top methods, including neural networks, for at least some of the domains, and they still retain the advantages of decision trees, which are interoperability. So you can still, because again, this is a bit more involved than just looking at a tree, but you can still go over all the trees and ask what is the questions that these trees are asking, or what is the most important question that these trees are asking, and what is the second most important questions, and so forth, and explain to your users why these trees, or how these trees work, which is very hard to do in support vector machines or in neural networks. So it retains most of the advantages of decision trees while doing much, much better in terms of classification compared to individual decision. Okay, so this is it for ensemble methods, or at least ensemble methods based on trees. As I said, this is very specific, right? Bagging and random forest are very specific for, bagging actually is a bit more general, but random forest is very specific for trees. We will have a class on ensemble methods that are more general and can be applied to trees, but can also be applied to other things later in this class. Okay, so this is it for decision trees and for ensemble. And now we are moving to the next lecture. And the next lecture is actually going to introduce a new type of supervised learning, which I mentioned, but we haven't discussed yet. And this is called regression. Okay, so until now, we focused on classification. Classification means that we obtain samples which have features, right? The features can be continuous, they can be discrete, they can be categorical, they can be whatever. But we obtain these samples, and our goal is to output a discrete value. Class 1, class 2, maybe class 1, 2, 3, or 4, or 5, but a relatively, the possible set of outputs is very small, usually 1 or 2, maybe 2, maybe a bit more, and discrete. Regression is different. In regression, our goal is to get samples. So we get, again, a training set with the features or the inputs and the labels, but the labels are now continuous. So they can be any number. Sometimes they're restricted to be only positive numbers. Sometimes they are really unrestricted completely. And the goal is to come up with a method that generalizes, right? So for the next sample, we'll also output some continuous value which best matches this input. Okay, so as before, we will have a training set, we may have a test set or cross validation, whatever, but the goal now would be to find the best continuous value rather than the best class for this data. And now, of course, regression is a whole, or regression itself is an important problem on its own. I will motivate it by some examples, but also, as you will see later in the class, including on Wednesday, regression can also be used as a component in classification. So some classification problems can be solved by first using regression and then somehow translating or using that result for classification. Okay, so even though we are talking about regression today, we are not completely finished, or in fact, we haven't, I guess we are only halfway through classification. So a lot of the classification methods we'll discuss later in the class will use regression as a component, even though the goal would be to do classification. But today, the goal is mainly on regression. So let's do an example, right? So let's say you want to choose a restaurant, but rather than, doing whether I like it or not, which maybe you like a lot of different restaurants, maybe you want to rank them based on some criteria that you have. But you don't really know which criteria to rank on, right? So maybe, sometimes, or maybe there's a lot of options, right? So you have what's the reviews for this restaurant, but on the other hand, some of them get very high reviews, but they're very expensive, or maybe they're very far, or maybe you personally, even though the reviews are great, you don't like the cuisine. So, you have some data that you collected over the years about your own preference, right? So for each restaurant, you gave a score, let's say 8.5, that's your own score. And now you go back and you want to come up with a score for a new restaurant that you haven't been to before. So how can you do that? Now, the score now is not whether you liked it or not. Maybe you liked all of them, but the score is how much you liked it, right? So now it's a continuous value rather than 0, 1. Because you want to rank and like, let's say you have 5 more restaurants that you can go to, you want to choose the best one. So how can we do this ranking? You look at the features, right? These are, if you look at the table that I'm showing, this is the score that I assigned, and these are the features of these restaurants, of course, and this is based on your previous history or your previous experience. And the goal is, you know, these are things, of course, that you don't need to go to the restaurant to know, right? You can see the reviews, like the price, the distance, and the type of cuisine, and you can actually rank new restaurants once you have this. Okay, so the goal is to take these different numbers and output a score that is as close as possible to the score that you actually gave it. Okay, so this is called regression. Basically, get the inputs like we did before with the classification, but now the output has to be as close as possible to a continuous value that we already get. Okay, so this is the goal. And this is not something, you know, this is not something extremely hard. I mean, people, or you have probably seen this before in linear algebra and in other domains. And the first example is something called linear regression, or the first of the method that we'll talk about in this class is linear regression. Although, as you will see, linear regression can be a bit more involved than just using the inputs and outputs to compute some relationship, but we'll get to that. So as we said, right, let's say we want to have, so let's start with a simple problem where we only have two values. One is the input and one is the output. For example, you tell me your height and I want to predict your age. Or you tell me the price of one stock and I want to predict the price of another stock. Or you tell me some reading of a sensor and I want to predict the real distance. Okay, so lots of problems where you have one input and one output and you want to have a function between them. So how do we do this? We usually represent this as a regression with a parameter. In this case, we can represent it by y equals wx if we assume that the relationship is linear. Linear means that the value of the output is a linear function of the input. And again, we will extend this later, but for now, let's assume that it's a linear function of the input. Okay, so when x goes twice as much, y will go twice as much. But it's not necessarily right? It's not necessarily one-to-one. So it's not necessarily that y equals x. It could be that y equals 3x, minus x, or something like that. Okay, so w is the parameter, and epsilon here means the measurement noise, right? So for example, if I want to predict a relationship between age and height, we know there is a linear relationship, right? As you get older, or at least let's say for the first 20 years, as you get older, you grow higher. But obviously different individuals are going to have different heights. So we cannot assume that everybody follows the same model. What we assume is that there is some model and samples can contain individual noise, right? So basically, for some people, this will be very good. For some others, it might be very bad. And so epsilon is basically not something we compute or observe. This is just an assumption that the model is not perfect. That because, and the model is not perfect for a lot of reasons. One reason is that it's not really a linear relationship. So we model something with a linear relationship, even though it's not, we need to allow for noise because otherwise we won't get, or there's no solution that will be perfect, right? If I take all the individuals in this class, I will never be able to learn one value that matches ages to height. That's not going to work. Or if I take, 20 individuals in different ages. So we need to account for the fact that the model is not perfect, and we account for that with the noise term. Okay, but assuming that this is the model that we have, that y equals wx plus epsilon, the next question is, so y and x are the inputs, right? This is input. Epsilon, we said, we just assume is noise. So the goal of linear regression is basically to find the value of w. What should be the value of w that will be the best, or that will lead to the best relationship between y and x? That's the motivation. But of course, what do we mean by the best relationship between y and x? How do you define the best relationship? So we are going to make an arbitrary decision here, which I will motivate in a minute, but it's only a motivation. It's not the only way to do it. So we are going to use an arbitrary decision that the best w for a specific input set is the w that minimizes the least square. Okay, least square means the difference between yi, of course, wxi, we want it to be as close as possible to yi. but it's not going to be as close as, it's not going to be perfect. We know there is noise. So our goal is to find W that minimizes the least square error. Okay, this is just an arbitrary decision. And as you will see in the problem set, that's not the only way to learn W. So you can learn W by finding the W that minimizes the absolute error rather than the sum of the absolute error rather than least square, or maybe some other function of the error. Okay, but for this class, and there is a reason why, but for this class, we will focus on least square minimization. So we will try to find the W that minimizes the least square error. Of course, minimizing the error is always good. The question is, how do we define the error? And in this case, minimizing least square error. And as I said, there could be several other approaches, but least squares is the thing that we will use. And I will mention maybe towards the end that this has a nice probabilistic interpretation. So if you use least squares, you can basically interpret the noise as basically a probabilistic object or a probabilistic function with some mean and some variance. Okay, we are not going to explicitly model it, but we can say we assume that the noise is a Gaussian-based error with mean 0 and some variance. If you use least square, if you use other things, then this interpretation does not hold. So that's why, or one of the reasons people use least square, but there are other reasons. I mean, as you will see, it's very easy to compute, unlike some other things that you will work on in the problem set. It's much easier to compute least square, for example, than to compute absolute error. So this is the thing that we will use at least for this lecture, and then also something pretty popular, or in many applications. That's the type of error, or that's the minimization function that we will use. Okay, so assuming we want to do least square, then the question is, what is the best W? And the answer is going to be, like we did before, this is not probabilistic anymore, but still we want to find the minimum on a function. So if we want to find the minimum of a function, we take the derivative with respect to the parameter. The parameter here is W, so we can take the derivative with respect to W and say that in order to find the minimum of this, we take the derivative with respect to W, so it's minus, I mean, the internal derivative times 2 times the parenthesis, and you know, you go through the math, and you get that the best or the optimal solution for W is sum over xi over sum over xi squared. Okay, so this is just the solution if we assume linear regression, or if you assume that we want to minimize the least square error, the W that will minimize the least square error is W that is computed in this way. Okay, just comes out of the derivation, and you can compute W. Okay, so this is good, and now if we want to find a linear relationship between two variables, that's how we would find the best, or that's how we will find the parameter for them. And this works pretty well. For example, if I generate some data, so I generated here some data where basically y equals 2x plus some noise. I generated Gaussian random noise with mean 0 and standard deviation of 1. And you can see this is the results. And they obviously the points do not lie on the line just because I added the noise. And if you use least square, you get something like 2.03, which is very close to 2 with a pretty small noise. So that's good. If you increase the noise, so if I increase the noise, you can see that the points are pretty far from the line. But still, the W that we get from least squares is pretty good. It's not, even though I introduced a lot of noise, and even if I even increase the noise dramatically, and you can see now that the points are very far from the line, or some of them are very far from the line, because we have enough points, if we use least square, we get a very good solution for W. Okay, so this works reasonably well if you have enough data and if you assume a linear relationship between the points. So if the model really is a linear relationship. Okay. So this is a regular or a general regression problem. So this, so far, we basically assume the linear regression, a linear relationship. Sometimes a linear relationship is not enough. For example, let's say that we have two stocks, right? Let's say Google and Apple. One is priced around 100. I mean, it's just a matter of how many stocks there are. And one is priced around 500, okay? So if that's the case, then when Google goes up 10%, Apple also maybe goes up 10%, but there is right. I mean, we want, well, I guess, yeah, so there might, let's say there is an additional term that we want to use to model the difference. So maybe or let's say, you know, let's forget the, let's say that for every year you go up, for every year in the first 10 years, you go up by 5%, okay? But of course, you start with some height. So you start with maybe 6 feet or 2 feet or something, and then you go up by these percentages. So we don't want to say that every year you are X% greater than what you were born with, because when you are born, this is like the baseline, and then from there you go up by, let's say, you know, with every year you go up by 10 centimeters or 4 inches. Okay, so in this case, we have a bias term. A bias term is this W0, which is independent of the X, and we have this shift in the results, which are so basically we want to model the outcome as Y equals W0 plus W1X. Okay, so we want to introduce a bias term that is not dependent on X, and then the value that is dependent on X. Okay, so, right, so you always, right, so if your age, let's say, goes up by 1 year, you go up by 4%, 4 inches, and if you go 2 inches, it goes up by 8 inches, but you always know that you started with 2 feet, okay? So you start with 2 feet, and then you add the inches based on the year. Okay, so this is also a linear regression problem. I mean, it's not, we didn't change the fact that we are multiplying the input by a linear term, we just added another parameter, W0, that we don't know. If we have enough samples, we can still do the analysis or do the least squares and find the best values for these two parameters. And again, it's the same thing, right? So we want to minimize now, rather than minimizing, rather than minimizing the least square for the, rather than minimizing the least squares for the original problem, we can write mean over W, sum over I, W0, Xi. Okay, so this is also a mean a least square, but now rather than assuming that Yi equals Wxi, we assume that Yi equals W0 plus W1xi, and this is the equation that we want to minimize over the square. And when we do that, right? So this is something that we can easily write, and when we do that, right? So when we write it as the optimization function that I just showed you, the results are going to be, so basically now we are doing, again, we take the derivative with respect to W0 and W1. We usually do it as a partial derivative. So first we take the derivative with respect to W0, and we get W0 equals this, Yi minus W1x over N. N is the number of samples, and I is the set of samples. Okay, so this is W0. And then we can, once we have W0, we plug it into the, we use it basically in order to compute W1, and W1 becomes sum over I, Xi, Yi, some function. Okay, so this is the regression problem for two parameters, right? W1 and W0. And we will give a simpler solution in a second, a bit more. But before I give the simpler solution, I want to motivate why we need. Okay, so this seems to be all we need, right? Either a linear term for one variable or a linear term plus bias. But actually, I mean, we can use regression for a much more complicated problems. For example, so far we did regression for a univariate model. Univariate means that I want to predict one variable or one value from another value, either with a bias term or without a bias term. But in practice, in many cases, I would like to predict one value from a lot of different, from a combination of a lot of different values, right? Let's say I want to predict the Google stock price, but why just use Microsoft stock price? You can see that this is old slide because Yahoo does not exist anymore. Good. Netflix still exists. it doesn't exist, right? Microsoft bought them, I thought. No? Anyway.
Verizon owns them.
Verizon, okay, so even better. Okay, anyway, but you know, you understand at least the basic idea, regardless of the mistakes. So basically, but the companies exist, but not as a standalone. That's what I meant. So let's say you want to predict the stock price from a lot of other stocks, right? So maybe a few 10 or 20, and again, this is something you will do in the problem set. But let's say you have a number of different variables, and you want to predict the value of a single variable out of all of them, right? So you have Google, and you have a lot of other tech stocks, and you want to predict that price. So this still is the linear regression problem, because each of the different stock prices is multiplied by a linear term, basically by a parameter, one individual parameter, which linearly multiplies the stock price. But now, unlike before, where we had one or maybe two parameters, now we can have up to, you know, depending on how many features you have in your input, we can have K parameters, K can be very large. So now, of course, we can start doing this partial derivative thing, which we take the derivative with respect to one, and then take the derivative with respect to another, plug it in. But that would be a very time-consuming and also not very efficient. It turns out that there is a simpler way to do it, or, well, I don't know if simpler, but at least a much more, a much better way to represent this and solve it in a one, basically in a one, or you can solve this problem not by doing this partial thing over and over, but by one computation. A single computation can find the values for all the different parameters, okay? So this is what we will do. We will talk about how to find, or how to, and again, the goal is to find the least square. So we are still trying to find the parameters that minimize the least square error between W and the sum that we compute, but rather than do it iteratively one at a time, compute the partial derivative and then plug it in and then compute the next one, we can do it in one shot. Basically, we will have a closed form solution for all of these values, okay? So this will be our goal, or this is the goal of the next few slides. Before we do it, I just want to mention that linear regression, even though we talked about the fact that linear regression only uses a linear combination of the inputs, it's not restricted to the values of the input. What do I mean by that? Let's say that I want to compute the relationship between your height and your age, okay? But in fact, your height is not really related to your age. It's related to your age square for some reason. Your age square is still an input, right? Because I don't need to learn any new parameter in order to compute the square value of an input. In other words, any transformation of the input that is predetermined, that is fixed, like taking a square or square root or log or whatever, is still an input. Of course, you need to define before you use it what transformation you want. But if you do a transformation of the input, it still remains an input as long as the transformation is fixed. So basically, linear regression can work, of course, on the inputs themselves, on your age, but it can also work on your age square if that's what you're using as an input. The point is that this is also a linear regression problem, even though it seems to us as a polynomial problem. But let's say I want to predict the Google price from the square root of Microsoft and the square root of Netflix. I can write that down, and this will still be a linear regression problem. So finding 10, 3, and 2 will still remain a linear regression problem. Why? Because once I know x1, it's easy for me to compute x1 squared. I don't need to learn anything. And similarly, once I know x2, I can compute easily x2 squared. So basically, the point I want to make is that any transformation of the input that is fixed, that you do before you learn the function or before you use the function, is still an input. And if it's still an input, this is still linear regression. So what is not linear regression? There are things that are not linear regression. We will talk about them next time when we talk about logistic regression. So not everything is linear regression. But any regression that multiplies the parameter by the input or transformation, a fixed transformation of the input that does not include any parameters that you learn, is still linear regression. And the reason why I'm emphasizing this is because the solutions that we give in a few slides to finding the best parameters for linear regression will also work for any transformation of the linear regression. Of course, you need to use the same transformation in the training and the testing, so you need to fix the transformation you're using. But once you decided on the transformation, you can still use all the methods we learned for linear regression for that. And that's good news, because now we have a much, much bigger class of functions that we can basically learn with linear regression. Okay, so as long as the coefficients, the W's, are linear, this still is a linear regression problem. Right, so this is basically a linear regression problem where you, instead of using x1, you use x1 squared and xk squared, right? Because before you actually learn the W's, you already do the transformation, and when you get a new sample, you can also do the transformation and use the W's that you learned for these squared values. Okay, so this is linear regression. And there's lots of ways to do it. For example, polynomial learning is linear regression, because you can do, let's say, y equals w0 plus w1 x1 plus w2 x1 square plus w3 x1 cube, and so forth. This is a linear regression problem, because once you have x, you can learn, or you can actually basically find all the exponential values of x for any value. Gaussian, so if you have a fixed mu and sigma for each of the features, you can also learn that. You can use other functions. Any function that is a deterministic value of the input is going to be a fair thing or a possible thing to do for linear regression. Okay, so this is important, and again, expands greatly what we can do with linear regression, or once we know how to find the parameters, which are the W's, that's the goal, to find the best value for W. This expands it greatly, because now we can assign it to any transformation of the input. So linear regression is more general than just the actual values of the input. Okay, so if that's the case, then we can write the linear regression problem rather than, as we did before, as sum of wi xi. Rather than that, we can write it as basically y equals sum of j equals 0 to n, where basically we basically expand the feature space to include 1, right? 1 is the value that we multiply w0 by, and other than that, it's all the transformed features. So w0 is multiplying 1, and all the others are multiplying some function of the input. It could be the input itself. So this can be just, you know, w1 times x, or it could be any transformation, x squared, x cubed, whatever you want for the j's feature. And the goal is to learn the wj's, right? The wj's are the parameters that multiply the different transformations of the features. Okay, so they can be the actual value, they can be a univariate, an identity value for example, for the stock, this could be just the price of the stock, or quadratic value of that, or whatever. Okay, so this is the general representation of the least square problem, right? So the wj stays the same, that's the parameters, and phi j is a transformation of the inputs. And our goal is now as now we go back to our multivariate problem, our goal is to find the optimal wj's, where optimal, in our case, is the wj's that minimize the least square. Okay, and as I said, there could be other ways to define optimality. In this class, we use least square to define optimality. Okay, so this is the general setting for linear regression. And now the question is, how do we do it? Sorry, now the question is, how can we find these W's? So again, this is the goal, right? We say that W or Y, sorry, equals Wj phi j of x. And our goal is to minimize this function, which is the sum of least squares, yi minus sum over wj phi j xi. Okay, so this is xi, of course, is the x input, and phi j is the jth feature, or the jth transform feature of the ith input. And the goal is to minimize. So this is the value we get from the regression. This is the input that we get for this specific sample. And our goal is to minimize the least square. How do we do it? We do it in the same way that we did for the...
Siv, I just have a quick question in chat. Someone's asking how we select the best phis.
Yeah, good. So that's a great question. There is no, I'm not going to provide, there is actually no way to select the best phi's. One thing that you should consider, and that's something that will come up actually later in this class, but also others. Let's say that you want to look at the relationship between y and x. Okay, just one value, x. Let's say age. You can represent age as a polynomial, right? So you can actually, from one value, so your goal is to predict your goal is to predict the height from the age, right? So you can use the age as one value, but you can actually represent it as 10 values because you can take age, age square, age cube, and so forth. So what's the problem with that? The problem with that is the more values you introduce, the more parameters you have. The more parameters you have, the more likely you are to overfit. So one thing you should worry about when you introduce these phi's is the fact that you can have lots of them. And the more you have, the more overfitting you can get. But other than that, there is no formula for which ones are the best. You know, as we always say, one thing is just to try, right? So for example, you can do cross-validation. If you want to decide, right, let's say in the regression for age thing, right? We don't know if we want to use age or age square or age cube. One thing you can do is cross-validation and test which one is the best for you and stop at some stage. Okay, so again, we will have, I think, a class on model selection and feature selection, and we'll talk about that. But that's one way. But generally speaking, there is no formula for assigning the best. When we talk about, so again, this idea of transformation is something that will come up again I mean, this is basically all the regression problem can use transformations, but it's especially important for support vector machines, which we haven't discussed, but we'll get to. And when we talk about support vector machines, we will mention a bit some ideas on how to choose the best transformation. And these can be applied to linear regression as well, although usually there's no good formula. You just either try or just do something that you think is good for your domain. The important thing for this class is that any transformation you want to use, you can still find the best W's for those. That's the point I want to make. How to find the transformation, not clear. Okay, so this is again the goal to basically find the best. Sorry, this is the goal to find the least square. And of course, the way we do it is we take the derivative with respect to W. Again, just to illustrate, so in order to do that, right, our goal is to find the derivative, or we said before, the way to do it is to take the partial derivative with respect to each of the Wi's, find the best values. Unfortunately, when we take the derivative with respect to Wi, we have all the other Wi's in that equation as well. So we need to somehow get rid of all of them together. So in order to show how we can do this, we are going to move to, rather than, this is scalar representation, right? Each W is one value, each phi is one value, and so forth. Y is one value. I'm going to move to a vector representation. So Y remains one value. So for each I have one value of phi. W is now a vector, a row vector. WT is a line vector, and phi is also a row vector, right? So when you multiply, W is a column vector and WT is a row vector. When you multiply a line vector with a row with a column vector, you get one value. So this is one value minus one another value, and this is okay. So this is just a vector representation of this problem, and we can do derivatives in vector space, in matrix space, and so on. So now we are going to take, the next thing is we're going to take the partial the derivative, but now not with respect to individual W's, but with respect to the W vector. Of course, the W vector itself is composed of a lot of different W's, but we are working now in vector space. When you work in vector space, things are pretty similar to how they are in scalar space, for those who are familiar with linear algebra. So basically, we take the derivative with respect to W. In that case, it means that we need to do 2 times the internal derivative of the parenthesis, of the value in the parentheses. In this case, this stays the same, yi minus wt of xi, and we multiply by phi xi, which is the internal derivative t. Okay, so this is now, this we already said, this is one value, right? This is a scalar. This is a vector, and the output is again a vector, right? Because we are doing it for all the W's. So the output is the basically the vector of all the W's, or the thing we want to minimize, the value for each of the W's. Okay, so this is taking the derivative on the vector space. Next, we want to find the best solution or the optimal values for W, and for that we need to, as always, equate to 0, right? Equate to 0 means that we equate it now, because this is a vector now. So we equate the 0 to the 0 vector. So all the rows in this vector have to be, all the columns in this vector have to be 0. Okay, so we equate this to 0, which is this. And when we equate it to 0, we can open up the summation, move things around. And we get basically, so basically we multiply this and we basically separate it into the sum. So this is Wi phi of xit, and this is Wt, which is here, which we can take out of the sum because it's not related, it's not dependent on I. Sum over I, phi of xi, phi of xit. Now, very important thing here. This is, as we said, this is a row vector. This is actually, what is this? Can anybody tell me what's this? What is this thing here? How does it look like? So what is, I mean, yeah, when I stop, but basically phi of xi, which is a column vector times a row vector. Yeah, no, right. So the answer is correct. It doesn't matter exactly what we call it, but as most of you, if not everybody who answered correctly, this is now a matrix. So now we have basically, right? So this is a row vector. So multiplying by a matrix will give us a vector, and this is also a vector. So basically, we get this matrix here, which is basically a function of all of the different inputs. Right? It's a function of all of the transformations, sorry, of the different inputs, because we are summing over. So this is a summation matrix of all of the inputs that we have. For each input, we create basic. So this is one matrix, and we sum over all of them to get the sum of these matrices. Oh, sorry. Am I sharing my screen? So what we get is this matrix. So each of these is a matrix, and the sum of all of them is basically the summation of the contributions of each of the individual components. Okay. So this is what we get. Again, so until now, I just copied it from the previous slide. And now we are going to take a big step that you will have to convince yourself that is correct. So if you define a big phi as basically, again, this is not any computation. This is just a matrix of the inputs, of the transformed inputs, as we said, for each of the samples. So this is the row for the first input, this is the row for the second input, this is the row for the third input, and so forth, right? So the sort sample, right? So the transformation of the first sample, the second sample, and so forth. You can actually write, so if you take this, you can actually write it as this part here, this summation, not the value itself, but the summation over all of the individual products is basically phi t times phi. Basically, each one here multiplies by this and summing over all of the individual components. So this sum here is phi t times phi. Okay, and this thing here is basically multiplying that by phi t. So if you take this to the -1, or if you take the inverse of this, you basically multiply this by this. Y, of course, you can represent as a vector. So if you represent this rather than as a sum, as a matrix, you actually get phi t phi times phi t times y, which in this case, y is a vector, so it multiplies individually each of the samples. Okay, so basically this part here goes here and inverse, and then you basically can separate W out. And then it multiplies, or this part here multiplies this summation here. And when you do it, when you sum over I of all of these individual ones, you get the product. So when you multiply this and you sum over, when you multiply this and you sum over I, you get the summation over all of the individuals multiplications, which is basically this function here. So phi t phi -1, phi t times y. And y again is a vector, so it's basically the vector of the samples. Okay, and W again is the input. So again, let me just explain in a bit and to show you why this is indeed doable. So first of all, we know that this is an n by k1 matrix, right? So n means If we look at phi, we have basically n rows, which is the samples, and k columns or k plus 1 columns, which are the features, right? So this is n times k plus 1. This is k plus 1 by n, right? It's k plus 1 by n because it's the transpose. So basically, this is k plus 1 times k plus 1 matrix. The inverse of this is, so this is, of course, a square matrix. When you multiply something by its transpose, it becomes a square matrix. And the inverse is still a squared matrix, which is still k plus 1 times k plus 1. This is phi t. Phi t is k plus 1 by n, right? Because that's the, when you multiply k plus 1 times n by k, or when you multiply k plus 1 by k plus 1 times k plus 1 by n, you end up with k plus 1 rows, sorry, k plus 1 columns, sorry, k plus 1 rows and n rows. Okay, so this, all of this here is k plus 1 by n, and then you multiply it by y. Y is a column vector of length n. So each row here is n, and this is n. And so we get output k plus 1 values. Okay, from all of this, we get k plus 1 values, and the size of w is, again, k plus 1 as well, k plus 1. W is basically the parameters, and we have one parameter for each of the features plus the w0, so k plus 1 feature. So at least in terms of dimensions, this makes sense. So this is k plus 1, k plus 1. This is n by k, this is k plus 1 by n, so this total thing is k plus 1 by n. And when you multiply it, we get k plus 1 values, which is the W. Okay, so using this, the important thing is that using this and computing, of course, you need to compute the inverse for this, but there is an inverse. This is the, we know that for this squared matrix, there is an inverse. So matrix times its transpose does have an inverse. When you get the inverse of that, you actually can get the value of W. And when you get the value of W, basically you solve all the partial derivatives together, right? So now we didn't take one partial derivative, plug it into the other, and then the other, and then the other. We basically found all of them together by doing this computation. Okay, so this is the way to solve, or this is the least square solution for linear regression. And this gives us a closed form solution. Right? It's important because in the next lecture, we will discuss other ways of doing it. This gives us a closed form solution, which basically provides the answer, the optimal value for the W for any of the transformation we use, right? So whatever transformation we use, we plug in that transformation into the phi matrix. And when we use that, and we have that, we can reconstruct the values of the W. Now, importantly, I should say, this is a good solution for linear regression because it solves the problem, but it might be time consuming. It depends on how many samples you have and how many transformation you did. Because taking the inverse is usually a cubic, it's cubic in the dimension of the matrix, or let's say in the dimension of the samples. Let's say if you have a lot of samples, and usually we have more samples than features. So this can be cubic in the dimensions or in the size of the matrix. And if, yeah, so, well, actually, sorry, I take it back. This is cubic in the dimensions that you're using. So if you do a big transformation, this would be, this could be very large. So if you use a lot of features, this can be a very large value. If you have relatively small number of features, this is going to be fine. Okay, but if you have a lot of features, this can be very time consuming. But still, I mean, once you do it, you actually can get the optimal solution. Okay, so this is it. Just to show you an example how we can use it. So here is a linear regression for a polynomial. So let's say I have, in this case, y and x, and I assume that x is a function of y. Sorry, y is a function of x, but I can do a lot of transformations, right? I can represent x as a 1-degree polynomial. If I do a 1-degree polynomial, then I have two parameters, w0 and w1. I can represent x as a 3rd-degree polynomial, and in that case, I have 4 parameters. I can represent a 5-degree or a 7-degree polynomial. And one thing you can see very clearly is the higher the polynomial value we get a pretty good fit for the points, right? So if I want to perfectly fit the points, I can use a very high degree polynomial, although the cross-validation is not necessarily as good. Okay, so but anyway, the important it's less important. I mean, we will talk in a second about this. But the important thing is that you can do it for any degree, right? Now that we have a general solution, you can fit any degree polynomial, 7 degree, 10 degree, 15 degree. You will get the best values for your input. As I mentioned, we wanted we use least square pretty arbitrarily. That's not the only thing you can do. You can use other things rather than least square. One advantage of or one possible explanation to why we use least square is that we can have a probabilistic interpretation for this function, and the probabilistic interpretation is that epsilon in this case is distributed with a mean of 0 and some standard deviation. If that's the case, right, let's say we assume that, and I'm going to do it for the univariate one, but it's the same for everything. Okay, so if I assume that epsilon is distributed with a mean of 0 and some standard deviation, let's say sigma square, okay, so this is just the assumption, then the maximum likelihood estimation, the maximum likelihood estimator for W is going to be the W that we found using the least square approach. Why is that? Because in that case, what's the so this is the probability, right? So what's the we can write the we can write now the likelihood of the data, right? L of the data given the model. It's just a product on the error, right? So we now take the error. So it's 1 over 2 pi sigma square. This E minus, and now what I'm writing is the difference between the error, Y minus, let me do it again. Okay, so this is the likelihood of the data, or this is a product over. This is the product over I of this, and when you take the derivative with respect to W, what you get basically is this part here. Which I mean, you take a log and you take the log likelihood and you take the derivative, you get this part here, which basically means that in order to find the best W, you have to find the least square error, which is this square here. Okay, so this is basically the reason why, if we assume that epsilon is distributed, sorry, if we assume that epsilon is distributed, this is why if we assume that epsilon is distributed with mean 0 and some standard deviation, we actually get back that the optimal solution is going to be least square. And this is basically true for using a regression with one variable, but also using regression with multivariate. It doesn't matter, because the probability is on the error. It's not on the W's, right? Because we assume that the error is distributed with some mean and variance, so we still get the least square in the exponent of the Gaussian function. Okay, and again, minus 0 because we assume that the mean of the error is 0. Okay, so this is the explanation of why, if we assume that epsilon is distributed with mean 0 and some standard deviation, the solution, the best W, or the W that maximizes the likelihood, again, right, we already motivated why maximum likelihood is a good thing. The W that maximizes the likelihood of the data is the least square solution. Although, again, as I said, there are other reasons to select least square. Not even if we don't assume any probabilities, it's just much easier to solve, as you will see in the problem set when you will try to do other types of solutions, for example, absolute. Okay, so this is regression. regression, you can use. Okay, let me stop here for 1 second, and let's do a poll, a Piazza poll, and talk a bit about the different transformations we can do, and what's the advantages and what's the danger that they can provide. Okay, so I'm releasing 2 questions on the Piazza, and you know, take your time. As I said, no grading. This is mainly for me and for you to see if you were able to. So yeah, take a few minutes and try to do. So there's going to be 2 questions today. Okay, so let's talk about these. And again, I basically showed similar example when I talked about the polynomial thing, but now we will talk about it a bit more formally. So basically, I asked you 2 questions about using linear regression for polynomial analysis. So let's start with the first one. So the first is, I'm asking you about learning a function where you get samples that have 2 values, x and y, and you want to and you can learn, because of the linear regression, you can learn polynomial of degree 5 or polynomial of degree 7. And you use the data to learn both polynomials, and you compute the error on the training set. And the question is, which will lead to a lower error for the training set, or which would likely lead to a lower error on the training set? And the answer is, almost regardless of what is the real, data that generated, so whether the data was generated polynomial of degree 1, 2, 3, 4, 5, or 6, or 7, or 9, polynomial of degree 7 will usually lead to a better result for the training data, as most of you determine. Why is that? That's exactly what I showed in the slide about the polynomial. Because even if you have data with a lot of noise, when you have a higher degree polynomial, the polynomial can fit the noise better. It's not the right thing to do, but it's going to fit the noise much better. So in that case, the errors that the polynomial of the 7th degree will make, even if it's really data from a 1st degree or 2nd degree polynomial, will be lower because it can fit to the noise. Of course, that's not a good general solution, but for the training data, that would work. Okay, so generally speaking, and that's true for a lot of different problems, when we have more parameters, and in the 7th degree polynomial, we have 8 parameters, right? W0 to W7, whereas in the 5th, we only have 6 parameters. When we have more parameters, usually we will fit the training data. Unfortunately, that's not what we are really interested in. The question is, the real question for us is, what will fit the general data better? So which degree of the polynomial will fit the general data? And in this question, the answer is, as again, most of you found out, number 4. So the real answer is that it depends on what is the data being generated by. If the data is really coming from a 5th degree polynomial, then a 7th degree polynomial will overfit, and it wouldn't generalize well. And that's also true for a 4th degree polynomial and a 3rd degree polynomial. On the other hand, if the data is coming from a 7th degree polynomial, then the 7th degree polynomial we learned will be better than the 5th degree polynomial, because it's really a function of a 7th degree. And that's, by the way, is also true if the data comes from a higher degree polynomial, 8, 9, 10. 7th degree is much better at approximating 8, 9, 10 than a 5th degree polynomial. So the answer is we don't know, because it really depends on how the data was generated. And that's something we don't really know, or we are not told at least. Right? So the answer is going to depend on how the data itself is generated. So the answer in this case is number 4. Okay, so this is it for this poll today. And again, as I said last time, if you got it correct, great. If you didn't get it correct, this is the first time, or at least for some of the first time you see this, or maybe you didn't, you didn't understand, or you didn't understand the question, or whatever. Don't take it too bad. It's not like you don't understand the class. Just go over the material after class, and of course in the problem set, you'll be fine. Okay, so let's go back to our lecture and discuss some other types of regression. So we talked about linear regression, but that's not the only thing we can do with the methods we defined. There are a lot of other types of regression. I'm going to talk about 2 that are pretty popular, but there's lots of other things. And the reason why I'm mentioning them is they use ideas similar to linear regression, but they don't use them globally. They use them locally. What do I mean by locally? Right now, we said, let's take the inputs, let's take the output, and let's find a global function that matches the input and the output. But that might not be the only way to do it. There could be ways where we learn local functions, so learn regressions that are only, or we are only going to use in a subset of the input. For example, let's say we want to predict y as a function of x. Okay, but I can have one regression function for x between 0 and 10, another regression function for x between 10 and 20, another regression for x between 20 and 30, and so forth. This is called the local regression model, rather than a global. And there are lots of different variants of local regression. One very famous example is something called splines. Okay, so splines are polynomials. We said linear regression is about polynomials, but unlike regular polynomial, as we said before, as I showed you, I'm fitting the splines to a subset of the input. So here I'm fitting one spline to values between, let's say, 0 and 10. I'm fitting another spline to values between 20 and 20, another one values between 10 and 20 and 30, and so forth, right? We can do it because we can just take, and that's pretty easy, right? We check the samples, we look at the samples, and we ask for which samples we have x between 10 and 20. We use those x's to learn the spline for that. And then we use the other x's. And that might be better because that might mean that we'll have a different function for different parts of the inputs, which can behave very differently. So that's the nice thing here, is that we learn a relatively small degree polynomial, right? So for example, in this case, we learn a third degree polynomial, which still fits the data very well, because unlike before, we don't need to apply to all of the data. If we had to apply to all the data, maybe we needed to use a 10th degree polynomial, a 20 degree, which is very dangerous, we already said. But now we can use a set of small degree polynomials to fit the data pretty well, even though we are only using relatively few parameters for each one. What's the danger with this type of approach? What can people think of a problem with this type of approach, with learning these individual polynomials? What could be a problem? Overfitting, yes, but let's assume that, you know, we have enough samples for each of the individual subsets. Exactly. So that's a big problem. A big problem in this model is that because we learn these polynomials for each section separately, what can happen is that, right, so let's sketch this here. So we can learn one polynomial here, which will fit pretty well and will be pretty smooth, but the second polynomial will start here and move here. And then the third one will start here and move here. So now, when we are at the boundary between two polynomials, we get a huge jump in the prediction, which doesn't make sense. It doesn't make sense that, I don't know, let's say this is 10, that from 9.99999 you have a value of 1, and then 10.000 you have a value of 5. That's not a reasonable function. Okay, so the continuity is a big issue for these local prediction tasks. What can we do? In splines, there is a simple, or not a simple, but there is a solution that people adopted, and that is to require that splines are continuous. What does it mean that splines are continuous? It means that the endpoint for this polynomial, or the value of this polynomial at 10, will be the value of this polynomial at 10. So they have to be equal where they meet. Okay? That's good, but it's not enough. Why isn't it enough? Because we don't just want to have equality, we also want to have continuity. We want to have derivatives that are pretty smooth. For example, if you draw this again, then these two polynomials actually are quite good in the sense that they have the same value at the intersection, but they are not continuous, right? You have a breakpoint where you have this big jump from one direction to the other, or basically there is no derivative, or it's right. The derivative here is basically infinite. So another thing that people require in splines and in other local regression models is that in addition to being continuous, the first and second derivatives are also smooth. Basically, they are equal. That means that when we have two splines that meet in one point, they have to be the same. The values of that point have to be the same. And also the first and second derivatives of these two splines have to be the same. What does it mean in terms of free parameters? So if I have two splines, I learn the value for this spline here. How many free parameters do I have for the spline on the right? If we define this as equal and equal in the first derivative and equal in the second derivative, anybody? How many free parameters do we actually have? So in total, cubic polynomials have 4 parameters, right? W0, W1, W2, W3. For the first one, we set the parameters. But for the second one, we said that it has to satisfy 3 equations. One is equality, another is equality of the first derivative, and another is the first equality of the third, if the second. If you write these equations down, you find out, as was mentioned in the chat, that you only have 1 free parameter for this. This means that this is another nice thing about splines, is that in addition to the fact that you have local polynomials, you don't have a lot of parameters, right? You don't overfit, as was mentioned before, because unlike with regular polynomials, we have a lot of constraint on the values that we can add. So rather than, we are not really adding 4 new parameters for each of the new splines we add, but instead 1 parameter. And again, this is splines with the degree, cubic degree. You can have splines with other degrees, which will lead to more parameters or different type of parameters. But usually that's the idea. But again, the key point here is that we're using local computations rather than global computations to compute the parameters. In addition to splines, there are other ways to do this. So splines are one way to learn polynomial, to learn local regression. There's also something called kernel regression. And kernel regression basically is the same idea. Rather than computing some global function, you compute local function. And now the question is, what do I mean by local and how do I compute the functions? For example, if you want to compute some average in a room, you can just take you can do measurements and a lot of points in the room and take the average value. But if you want to compute an average at a specific point, if you want to compute the temperature at a specific point, maybe it's better for you to do the averaging not for all the points, not a global average, but rather a local average, right? So you want to compute the local average at this location.
Ziv, there's a quick question in the chat. Someone says, is the single free parameter the reason why cubic splines are most common?
No. So cubic splines are indeed the most common, but you can actually have 1 free parameter for a 4th degree polynomial if you require also that the 3rd derivative is the same. So it's up to you to make the requirements, right? So it's up to you to say how many free parameters there will be. So you can do 4th degree, 5th degree, and just continue to make requirements on the similarity or continuity. I think the reason why cubic polynomials are useful is because if you think about the way functions can represent things, then a linear functions can only go up, a quadratic functions can go up and down. A cubic is really the first that can have multiple endpoints. So if you divide the data into small enough regions, then a cubic polynomial usually can fit most of the potential functions. So that's why they're pretty popular. But I don't think there's a big theory about why cubic, but indeed cubic splines are usually the most popular spline methods. But again, cubic splines and their use is very common in graphics and other domains, less so machine learning is, it's not as useful in machine learning as in other domains. So I don't want to talk too much about it. Again, I'm not saying it's not useful, it's not being used as much. Let's put it this way. It's very, very useful. Okay, so we talked about a local regression model for splines. We can also do local averaging, right? In this case, rather than taking the average on the entire room, we can take the average on a subset of the points. Does this remind anyone of some other algorithm we learned? That takes the average in a specific location rather than taking it on. Yeah, exactly. So this is very similar to the idea of KNN. But again, KNN is, as we said, KNN is a supervised learning method for classification. Now we are talking about supervised learning regression for regression. So like we did in KNN, where we took the majority vote in a location, we can do the average value or the average regression for a specific location. So this is the idea of kernel or local regression. The word kernel basically in this case, and it will be used in other notations as well, but the word kernel here means the area around the point that we are interested in. In this case, I'm taking some cutoff based on the distance between the points. I'm using all the points within this specific ball to compute the average, and all the points outside I'm excluding, but I'm not giving different weights to point based on distance. That can also be done, okay? So this is rather than computing the global regression, for example, 1 over n for all the points, I can compute the local regression, which is 1 over n just for the points within my region. Okay, and I have a bit more to say about that and about kernels, but we'll finish this next time, and we'll move to another type of regression, which is called logistic regression. Okay, so that's it.